Okay, so we're going to get started. It's my pleasure to introduce Hong-Lek Lee. Hong-Lek finished his PhD at Stanford University with engineering in 2010, and he's a professor at University of Michigan, and he's also spending a little bit of time now at Google Brain, and he'll tell us about deep reinforcement learning with forward prediction, memory, and hierarchy.
So thanks, Sergey, for introduction, and also thank you for everyone coming early in the class this morning. So I'm going to talk about three line of work that I'm doing at Michigan and also at Google Brain. So these are the three themes. So the first question is how making prediction or building a model so that you can somehow simulate this future can be useful for reinforcement learning. And then second, I'll talk about how memory can be useful for developing deep RL agent, especially for first-person view environment that maybe a robot has to operate and is relevant to also real-world physical scenarios. And third, I will talk about some work on hierarchical RL architecture that can be useful for generalizing in multiple tasks and also following instructions. So for the first piece of the work, maybe some of you have seen this before. So this was originally published at NIPS 2015. So our problem of interest is how to make a long-term prediction in the future and how to make it useful for reinforcement learning algorithms. So the main idea here is that we want to build a model. So for example, given some past observations and given some current action, you want to make a prediction over what will happen. It turns out that previous work before this somehow focused on just building a model for the videos without considering action too much. So in this work, we basically show that combining this convolutional architecture with action is actually useful for making long-term prediction. I should maybe give you a caveat that long-term in a sense that we can make a good prediction on simulation videos, but to make it work for real-world video or real-world scene turns out to be much more challenging. So I'll also talk about some ongoing work, how to predict well for some real scenes. So here's some architecture we developed. It is using some kind of convolutional encoding. It takes several frames, past observation, and then encode into some fixed dimensional vector. So this fixed dimensional vector represents some abstract notion of what's going on in this context. And then you consider some action as a transformation. So you can consider some kind of tensor product between this fixed dimensional encoding of the context and the action the agent takes. And then it tries to predict the encoding of the future next frame observation. And then you decode it back to the pixel frames. And then you can use it to feed into your model. So you can just keep predicting the future by just repeating this process. So this architecture turns out to be very, very effective in making predictions in the videos, like simulation videos such as Atari games. So this is actually just taking some fixed number of past frames. And it is actually also reasonable to consider some recurrent architecture. So you can consider some LSTM that takes some recurrent updates for this context. Then you just take less video frame and then you encode it into some vector, but then combine with the context. And you can still do similar action conditional update for the future. And then you decode it back, and then we can repeat this process to make multiple frame predictions. I should say that many similar architecture also have been proposed recently, and also they seem to work quite well. And I'm going to just show you some example video predictions for these Atari games, which is actually quite popular for reinforcement learning benchmark. So this game is called Freeway, and I'm showing the prediction on the left side and the ground truth on the right side. The algorithm is given the action that the agent takes, so it is given the actual exact sequence of actions, and then it is just trying to make a prediction. So you can think about this deep architecture as some kind of a simulator. It turns out that it's making really good prediction for this game. And basically the reason is that the system, this dynamical system is deterministic. So when, for example, the car moves to the end of this road, and then it will reappear on the right side, and so on. So it is actually 100% predictable without any uncertainty. So in that case, somehow this network has learned to nail down this problem very, very well. So it's actually making up to 500 step prediction, and then even then it's making really high quality prediction at the end. So this is the case when you have a relatively simple dynamics without uncertainty, and it does really well. But of course, when there's some more uncertainties and also more complex like movements of the agents and other objects, it's actually harder. So in this case, the agent is able to make prediction about its own ego motion. It's actually quite reasonable because you are given the actions that the agent is taking. So at least it should be able to predict how it will behave. But of course, it has some more errors in predicting other objects that it doesn't have control over, such as movements of the enemies and so on. But still, it's able to predict like some events like scoring or decreasing oxygen, and also increasing the oxygen when the agent goes up on the top of the water to recharge the oxygen. And here's some other games called Space Invader. So again, you can see similar kinds of qualitative results where we make some pretty good predictions, especially like destroying the enemies. But sometimes it makes some mistakes in terms of not predicting the weapons, or sometimes it does well, but sometimes not. But again, this is quite, yeah. To me, it was quite impressive to see this type of results. But the caveat is that this is a simulation, so yeah, maybe the game itself is not as complex as the real sceneries. And here are some other games. Again, in this case, the agent is able to make a really good prediction on ego motion. So it's able to predict how the Pac-Man will move, but the movements of the enemies is much harder to predict. So it'll somehow, the movements of the enemy will somehow become more unpredictable or becomes blurry at the end. So these are quite good prediction at the end. So we wanted to check whether this ability to make a prediction is useful for reinforcement learning scenarios. So the high-level idea is that we want to somehow guide the agent so that it can take advantage of this future prediction. The main idea is that we want to take on action so that the agent can do better exploration or explore more novel states or novel observations. So you can just take some previous history into memory, and then you can consider some kind of simulation. So given the current state, you just try out all the possible actions, and then you can at least make a one-step prediction. And then you try to pick an action so that it actually has least similarity to your memory. So you can simply define some simple kernel function that measures the similarity between your future predicted states and the past observations. And then you just pick the action that somehow leads to the most novel observations. So the main rationale is that by doing so, you can somehow help the agent explore the environment more aggressively. And also, when the agent is somehow failing in a repeated way, because it doesn't really know how to take a proper action, then basically doing this type of exploration at least helps the agent to avoid some kind of repeated failure modes. So for example, when you consider a game like Pac-Man, the agent has to move around this maze, and obviously if it tries to move past the wall, it will just stuck there. So nothing will happen if you somehow take an action that is not really consistent to the actual shape of the maze. And so if you just start with a random agent, then it takes at least a very long time to figure out how to explore, or at least how to take an action so that it doesn't actually get stuck in the wall. However, if you are able to make a future prediction, you can do this type of exploration much better. So this is one example how informed exploration can be useful. And also it turns out that informed exploration is useful for handling very long delayed rewards. So I'm going to show you some video here. So basically here we are comparing two versions of the agent, one with random exploration and the other with informed exploration. So left one is informed exploration and the right one is random. So the high level idea here is that for this game called Freeway, the agent has to basically start from the bottom. The chicken here, it has to start from the bottom and it has to reach to the top without being hit by the car. So when it gets hit by the car, then it has to restart from the bottom. So which means that if you start from random policy, then it will actually make a lot of mistakes before it somehow figures out that it's a good thing to move to the top. So it will basically repeat lots of failure modes because it doesn't really know what to do. And also, it is a challenging game in a sense that the reward is very long delayed. However, using this informed exploration, because it's trying to somehow explore more novel states, it is able to explore this much better. So because the chicken can either move up or bottom, up or down, so it somehow quickly learns to just go to the end of the highway, and as a result, it learns much more quickly. And similarly for the game of Pac-Man, it actually learns to explore this environment much better because it somehow knows how things will work, or at least some dynamics will work in this type of world. So in terms of some game performance, using this informed exploration turns out to be useful for certain games such as Freeway or Pac-Man or Qbert. So this gives some evidence that being able to make a future prediction is useful. But I should, yes?
So when you use the prediction model for exploration, are you using how did you train the prediction model? Did you train it on like random data or on like an expert agent data?
So we tried both. For this version, we actually used the data coming from the reasonable agent, so DQN agent. I should say that this result is actually asymptotic performance. So even if you train a DQN very, very long time, it still achieves worse performance than using this informed exploration. But obviously, this is a basic DQN architecture. So maybe if you use the most state-of-the-art DQN, it may actually perform better. But the high-level idea is that being able to make a future prediction is actually useful, even in asymptotic scenarios. And here is the visualization of the learned model. So we are visualizing the tensor weights for different actions. So for example, as a recap, there is some kind of three-way tensor here. So before taking an action, you have a fixed vector, and then you have some action-dependent tensor, and then you have a next action. So if you consider tensor weight, then you can visualize the similarity between the actions. So not surprisingly, the model has learned some implicit similarities between different actions. So for example, white arrow and black arrow just means moving in certain direction with or without firing a weapon. Somehow it has learned that the two movements with or without firing weapons are still kind of similar action, and also it has learned similarity between movements in some similar orientations. And another very interesting thing here is that this is a modeling the dynamical system, and there are two types of dynamics. So one is ego motion, because you have an action, and then it typically controls how your own agent will move. But at the same time, there are some uncontrollable part of these dynamics, such as movements of the enemies and so on. So it turns out that if you look at these tensor weights, we can just visualize some of the tensor weights that are highly dependent on the action. So if the tensor weights varies a lot depending on different type of action, then we can consider them as some kind of action-dependent dynamics. But there are also some tensor weights that doesn't have much variance according to this action. So in this particular scenario, the submarine is trying to move to the right and fire a weapon. So I'm showing the previous frame and the next frame. And this is what the agent predicts. The model is making prediction pretty well. And if we actually look at the visualization of these action-dependent factors and then zero out the rest, then it is actually making prediction of the submarine where it's somehow turning to the right. So it's actually correctly predicting that. At the same time, if you just zero out these blue parts and only use the red parts to predict the future, then it makes a blurry prediction for the submarine, but also it is able to make prediction for the enemy motions and other things. So this gives some anecdotal evidence that the model is able to learn some kind of controllable dynamics and uncontrollable dynamics and so on. So investigating more along this line would be an interesting question. I have shown some promising results on games, but it turns out that making this work for the real scene is actually a really hard question, especially when the background is moving or when you have some kind of more variety of motions and so on. So for example, when you consider, yes?
So I just want to check, you didn't incentivize the network to kind of learn these different factors, right? So you just look at the weights to see, and you just said if it has a small weight, then it must not be very action dependent?
So yeah, we didn't incentivize the network to do this type of distinction. So this is sort of a, I would say, emergent property. Somehow it learns this implicitly. It might be interesting to consider some more explicit separation to do this type of job. But yeah, we haven't gone too far investigating this yet. But this may be also relevant to maybe distinguishing foreground and background in vision, and it's actually somehow a good connection to that. Yes?
What's the intuition for how this tensor product dynamics is different from like a linear model or a time-varying linear model?
So I would say it's quite similar. I mean, if you can think about this as just a three-dimensional matrix. So you have one dimension which is about the previous frame's feature vector, and another for the next frame's feature vector, and also you have a vector representation for the action. So then you have a three-dimensional tensor that represents this transformation. And in that case, if you fix the action, then it is the same as just multiplying a matrix to the previous feature vector. So you can think about this as some kind of linear dynamical system. So if you have different actions, then you can consider this as a maybe k different linear dynamical system for the k different actions, because we can represent the action as one hot encoding in k-dimensional vector. So yeah, that's how this connects to the linear dynamical system. But I should also say that at the end, when you make a pixel level prediction, you have to go through this convolutional decoding that actually take care of very, very complex interaction between this feature vector to the pixel values. Yes?
Yeah, I was wondering, so did you notice that, I guess, the non-action factors were kind of consistent across different states? So was it always the same weights that were, non-action dependent?
So these non-action dependent factors just have a very little correlation or variance. So what we do is to check how these weights depends on the different actions. And so this is a three-way factorization, and there are some more details, but non-action dependent components are really not much dependent on the action. Okay. All right, so I'll just switch gears a little bit to just talk about some ongoing work for making predictions by incorporating some ideas of how to decompose the motion into some kind of content and movements. And also I'll talk about how to make a better prediction with some kind of more hierarchical way. So this is just for making predictions, and this could be useful for building a better model for a general RL agent, but the work itself is mainly about how to make a prediction in videos. So one idea is that you can basically consider some decomposition of motion and content. So the high-level motivation is that you can just consider the content about the last observed frame that somehow represents the appearance or shapes and so on. But at the same time, there could be some component that represents a motion. So we basically consider this separate decomposition, and then for the motion, you can consider some recurrent connections. So you can just explicitly take the difference between the two consecutive frames to somehow ignore the content as much as possible. So this basically models some motion components, and then you do some encoding of this motion, and then you combine with the last observed frame, and then concatenate them, and then just go through some decoder. And this is somewhat also motivated by neuroscience phenomena, where we know that our brain has two different pathways, one pathway representing the object or content, and another pathway that represents the motion. So we thought that it might be possible to model this separately and then just combine this together to make a prediction over the future. And since we also need to deal with some static background or things that don't change too much, it's also reasonable to consider some kind of residual connection, and also it is reasonable to consider some kind of multi-scale architecture. So to just show you some results, these are results on some relatively simple data set, such as KTH or Weismann. The high-level take-home message is that this architecture is able to model some kind of periodic motion quite well, probably better than the existing very strong baseline called convolutional LSTM. So this type of separate decomposition of motion and content can be useful here. We also evaluate on some more challenging real action data sets called UCF101. And again, similar conclusion can be made. And I would say this is a very, very challenging. So even our model is not really making a very long-term prediction. We can make maybe up to like 5 to 10 frames reasonably, but after that it gets quite blurry. So, but still we can see that compared to other strong baseline, our method seems to work much better. And here are some additional results. Again, I mean, we are making some several frame prediction reasonably, but then, yeah, but it's much better than the other existing work. And here's some quantitative evaluation in pixel level, and it just shows some comparison. Yes?
So the big difference between the game scenario and this scenario seems to be that the amount of data in UCF is just tiny compared to the game.
That's right,
given
yeah.
The complexity.
Yeah.
Have you tried to just push more data?
We haven't really tried. I think that's a great question. But I would say that also the variety and diversity of motion is much more higher. So yeah, probably with much larger data, it might be able to do better. But it's quite challenging to push with.
Well, it's challenging in academia. In Google, it should be easier.
Yeah, so that's actually what we are trying to do.
Very good. Very good.
But I will switch gears just a little bit to also talk about another idea that can possibly like dramatically improve this future prediction. But this is for the context of some specific domain where we know some structure of the data. So the high-level idea is that, for example, if you are trying to predict the future videos of human motions, it is actually reasonable to consider some kind of structure, such as how the human body skeleton will move. So the idea here is that if we just do like prediction that incorporates this structure as an intermediate variable, then we can keep the structure very long term, and also at the same time making a prediction in this structure space is arguably easier problem because this structure is lower dimensional and it has a less risk of getting blurry or like dissipate over the future. So in contrast, all the previous approach typically just assumes some kind of pixel-to-pixel prediction, and usually you can make a good prediction in the next frame or next 2 frames, but then it gets blurry and blurry, and you can lose structure very quickly. We are going to put archive report very soon about this work. So the high-level idea is that you consider some kind of this hierarchical decomposition where you predict the structure. So in this case, it's just a human pose estimation. So you can consider some estimated pose from the input frames, and then you use this past pose trajectory as an input, and then you use some LSTM to make a long-term prediction on this pose space. And then you can also do some pixel-level conditional generation given the predicted pose and previous pixel-level input, and also corresponding pose, and so on. So this is sort of a two different problem. One for predicting this future pose in this high-level structural space, and then you make a conditional pixel-level generation given this predicted pose. So the results are actually very promising. So these are actually end-to-end prediction where we make prediction on some sports activities. So compared to the baseline, our model is able to retain some structure of the motion much better. So again, it's not making a perfect prediction, but you can see that at least it's more perceptually plausible, and we can see that at the end of the prediction is still somehow recognizable as a human body. Okay, and here are some results on other data sets. So this is called human 3.6M, and this data set is more challenging in a sense that the type of motion is more diverse and also less regular. So in this case, actor is just behaving in a room, but without a very specific action like sequence. They can just behave in somewhat more random way. Even in this case, our method is still able to make a pretty good prediction, and it doesn't lose the structure even after like 100 steps. Somewhat more striking result is that we can also make a future prediction even longer if we had been given some ground truth trajectory. So this is sort of a control experiment to just check how well we can predict if we knew the ground truth pose trajectory. It turns out that we are able to make prediction almost indefinitely over the future. So I'm showing the actual ground truth video and our prediction, yeah, it's making like several hundred steps prediction quite well. So this means that basically retaining some structure is very important and can be very useful for making a long-term prediction. Maybe some limitation of the work would be that first, we are considering some specific domain, so we need some kind of knowledge about this domain. So how to generalize to very unstructured scene or arbitrary data is a very interesting question. But one take-home message is that structure is very, very helpful. Yeah, yes?
So you said that so this one is using the ground truth, but the previous one, the one
Right.
that's sort of the full model, it was using predictions of the pose.
Right.
Do you have any kind of idea for like how accurate those predictions actually are?
They are I would say they are plausible. I mean, again, there are some uncertainties in this future trajectory. So, so we have some quantitative evaluation, and the main take-home message is that because of this uncertainty, L2 may not be the perfect measure for evaluating the performance. So we are still investigating what is the best way of measuring this prediction performance, even in the pose space or structure space. But ideally, I think that if we have a stochastic prediction model, then we can maybe calculate the log likelihood, and maybe we can measure this in a more principled way. If you're only making one prediction, then it is very challenging, and maybe good performance in L2 may not really correspond to good likelihood or good model. So, all right, so so maybe I'll just switch gears. So I just talk about how some kind of forward prediction can be useful for reinforcement learning, and also I talked about how this can be made better by exploiting some ideas like structure or some motion content decompositions. So I'm going to talk about how memory can play some role in making better decisions for reinforcement learning. So one important aspect of building a real world agent is that there is a notion of active perception, where you have an agent that can somehow decide to proactively pursue different type of observations. And also, because you are not given the entire world as just a single shot observation, usually we need to somehow take information from many different time frames and make an informed decision to behave well. So some notion of memory would be important for these problems. And also we want the agent to generalize well to unseen environments. So this is an aspect that's maybe not too heavily explored in some work in reinforcement learning. So usually you would train and test in the same environment and then measure the performance, but we are actually interested in just training in one environment and making it work for the new environment that's actually different from the training setting. So these are actually quite hard to just do all these three things in some existing benchmarks. So we came up with some environment based on Minecraft. So in this case, the agent is always observing the first-person view environment, such as some maze with some objects inside. So the center figure basically shows some example of the observation. But the agent is actually behaving in some world that has some different objects and maybe goals that gives you rewards and so on. But this actual full view of the world is not available to the agent. So the agent just sequentially observes this type of first-person view and has to make an informed decision to maximize the reward. So this is actually a very flexible environment where we can just build some different reward structure or also different tasks and also put some different objects and so on. So we believe this is a very useful benchmark or test bed for the future work. So I'm going to explain some of the model architectures that we have considered. The simplest architecture will be the DQN. So in this case, it will just look at the past frames and then map it to a context and then make a decision about what action to take. And so this is a most standard architecture that actually works reasonably well in many different domains. But one difficulty here is that the agent has to generalize when observing some very long delayed reward. So for the case where the time scale of this delayed reward is much larger than the size of the memory, then the agent can suffer a lot because it doesn't really have a notion of the past event that's relevant to the current action. So in order to address that, you can also consider putting some recurrent architecture here. So you can just recurrently update the context, and then so you can simply just replace this context with some kind of LSTM, and then it will take an action. So this is probably a better architecture for handling some long delayed rewards or some very long temporal dependencies. But it doesn't have a very explicit or like sort of a photographic memory, so that could be some potential issues. So there are some recent architectures called memory network. In that case, you can simply just store the observations into different slots in the memory. So for example, we consider a network called memory queue network. In this case, you just have some encoding vector for the context, and then you just store them into different slots of this memory. And then when you make a decision, you just use this memory and retrieve the relevant one to the current context and make a decision. So this is some kind of combination of a so-called memory network and deep queue network. But then we can also consider some additional variations, such as making the context being like recurrently updated. So these two are memory network extension for these first two architectures. Also, we considered another architecture where the retrieved memory also can update the current context. So the difference between the recurrent memory queue network and feedback recurrent memory queue network is that there is a feedback connection, so that you update your context based on the retrieved memory. So roughly this last two architecture perform quite similarly, but we found that the last architecture is still the best one. It somehow makes sense that you would want to update your context based on what kind of memory retrieval you do. So I'm going to just explain some test bed and benchmark that we evaluate these models. So this is a very simple environment called iMaze. And in this case, the agent is given some indicator signal in the beginning of the episode. So here's an indicator block. And this indicator can be either green or yellow. And depending on the color, if the indicator is green, it has to go to blue. And if it's yellow, then it has to go to red. So the high-level idea is that it observes some important signal in the beginning of the episode, and the agent will go through the corridor, and around the end of this corridor, usually it's longer than the size of the memory or the size of the time frames for the DQN. So baseline models will have some difficulties in performing the right action. Whereas if you have some memory, then potentially you can use this memory to make an informed decision when it matters. And also we investigated whether the agent can generalize when it's trained for different size of the maze and then tested on some larger size maze that's not seen in the training time. So the high-level idea is that we need the memory because when the agent sees either blue or red goal, then it has to make an informed decision based on the indicator block. So for example, when the agent sees the blue block, then it has to somehow retrieve what it has seen in the indicator, and depending on the color of the indicator, it will need to make a decision accordingly. But of course, there are some cases where this initial observation may not be important, so somehow you need to retrieve the relevant memory slots when taking an action. So the experimental result is basically that our architecture that has this explicit memory and also with some feedback connection performs the best compared to baselines such as DQN. Actually, memory queue network performs quite well because it's relatively simple task. We found that having some recurrent connection actually is the best one. And here's some visualization of how the attention mechanism behaves. So in the first frame, this is the observation. And in the second frame, it basically stores this observation into different memory slots. So basically, these different rows represents the different time steps. And obviously, as you have more observations, then the size of the memory increases. And so you can think about the color-coded map here in a row as a sort of a relative strength of the attention. So somehow it's putting some high attention weight for the first frame because so far nothing important is happening. But as the agent goes around this environment and when it sees goal blocks like this, for example, when it sees the red color block, then it has to somehow remember what it has seen as an indicator. So now you can see that at this row, the attention weight, I have a sharp focus that correspond to this indicator block. Basically, this somehow shows that the network is able to retrieve the relevant information from the past observation when it's needed. And here are some video demos. And when the agent starts the episode, then usually it will try to look at the indicator block as an observation, and then it goes to the end of the corridor, and then it will make an informed decision based on the indicator block it has seen initially. And here are some other tasks. So in this case, we are interested in whether the agent is able to somehow remember and compare different patterns. So here, if the two room layouts are identical, then the agent has to go to the blue block. But if they are different, then they have to go to the red block. So in this case, the agent has to be able to compare two different patterns. So look at one room layout and look at another room layout and somehow make a comparison. And so we found that this type of comparison can be done through some recurrent architecture. So it's some kind of interesting nonlinear interaction between observations. And again, we found that using this feedback recurrent memory queue network is the best for this task. Especially when we look at the generalization scenario, when the agent is trying to behave in an unseen environment. Again, the generalization performance is the best when we have this memory architecture with some recurrent feedback connections. And here are some video demos. Yeah, the high-level idea is that the agent is trying to look at quickly one room layout and the other room layout, and then it will make a decision based on whether these two are the same or not. And this is another task based on random maze. So in this case, the maze layout is randomly generated, and we consider a different type of tasks. So basically just going to some specific goal, but we consider some variations such as sequential goals, which means that you have to first go to the red and then go to the blue. And also you have some goals with indicator. So depending on the color of the indicator, you need to go to different colored goal. And we consider sequential goals depending on the different color of the indicator. So take-home message here is that, again, using this type of memory architecture with recurrent feedback connection seems to perform the best. And the task itself is actually quite challenging, even with the memory, because we only have just the first-person view style memory. So it can be useful, but it's not really building on explicit representation of the map. So it has some limitations in exploring, but the message is that it can perform much better than just the baseline models without memory. And here are some additional quantitative evaluations, just showing some learning curve, and also evaluation curve in different stage of learning. But I should say that probably for the task like navigating a maze or 3D environment, probably building some explicit representation of the map is a good idea. So you can consider some kind of SLAM-like techniques or building some explicit 2D layout of the map. And I believe that Jitendra Malik's group have some upcoming paper about memory mechanism that's maybe relevant to this work. And here are some video demos. Again, the agent is somehow able to find the right goal, but again, it's not really having an explicit representation of the map, so somehow it is doing some kind of random exploration, but still at the end it can find the right goal. So obviously having some explicit memory mechanism would definitely improve the performance. Okay, so far I talked about how memory is useful for agents that are behaving in a first-person view environment, or in more generally behaving with parser observability. And it seems very plausible component that a good deep reinforcement learning agent should have. So now I'm going to talk about the third piece of the work, where we are trying to push this to more challenging scenarios, where the agent is trying to perform multiple tasks and also some kind of sequential orders. So the motivating scenario would be that when you build some personal assistant robot, usually human user can provide some instructions. So you can ask the robot to maybe go to a kitchen and pick some food, and then, or maybe pick up some clothes and put it into laundry room, or just pick up some object and bring it to you, and so on. So assume that the human user can provide some kind of sequential instruction or some kind of to-do list that the robot should execute in a sequential way. We want to make it generalized in two different scenarios. One for handling some unseen combination of the action and the target object, because For example, when you train a robot in a company, you would have some fixed set of training data, and probably it's practically infeasible to consider all kinds of combinations of the actions and the target object. So if you make the robot to be able to go to certain locations, then you want it to go to any arbitrary locations in the testing time. Similarly, when the robot is able to pick up some type of objects, then you want to make it pick up any arbitrary objects, or at least know some notion of this picking up, even in the case that it sees some unseen target objects or some new combination of this action and target. Okay? So that's the notion of a multi-task generalization in this work. So we consider a specific combination of action and target object as a specific task. And then we provide some subset of all this possible combination. And then in the testing time, we want to make it work for unseen combination of this action and target object. So that's one generalization problem we need to solve. Another generalization problem we need to solve is that, again, in the training time, you would give some number of sequence of actions to take. But then in the testing time, you want the robot to really solve the question that involves any arbitrary sequence. And also, you don't want the robot to just ask for feedback every time step or every time it finishes its subtask. So the agent somehow needs to figure out that it is done with one specific subtask and then move to the next task and so on. And then maybe at the end of the episode, maybe you can provide a reward about how well it did for this sequential instruction. So that's the two type of generalization that's inherent in this scenario. So just as a recap, this is one generalization problem, which is given some specific subset of this action target object combination, you want to make it work for unseen combinations of this action and target. And similarly, you want to make it work for any arbitrary sequence of instruction without having to give intermediate feedback about the subtask completions. So that's the second generalization problem. Obviously, we want to make it work for also very long sequence of instructions as well. So in our experiment, we train on like length 4 sequence of instruction, but in the testing time, we try to evaluate in much longer sequences. So one challenge in this second problem is that agent is not really given some intermediate feedback about whether a specific subtask is finished. So it has to internally know that it is done with the task, and then it has to move on to the next task without getting feedback. Also, there is some scenarios where if there are some random events or some kind of interruption that the agent has to handle, you can imagine a scenario where maybe it has to deal with some emergency situation or maybe some situation that it can get some random positive rewards, and probably the agent needs to be flexible enough so that it can somehow stop what it's doing and then deal with these random events. And this one is something I just talked about, being able to deal with unbounded number of instructions. And the reward is very delayed because it doesn't really get actual reward until the end of the episode. And here are some related works. So there's a lot of work on hierarchical RL, increasingly more work these days. And also some work on task generalization, such as universal function approximation. So our work can be viewed as some combination of these hierarchical RL that can do task generalization. And also there are some line of work for instruction execution, and our work can be viewed as some deep architectures for doing this. So here's the architecture that we developed. So the idea here is that there are two types of RL agent. One is called subtask controller that is able to generalize to this type of arbitrary combination of action and target object. And so it has to deal with the first generalization challenge. And we have a meta controller, which is taking the sequence of instruction and then somehow controls this subcontroller and provides some command to execute and then move on to different part of the instructions and so on. And these two agents can communicate through some kind of compact protocol. So in this case, meta controller gives some signal that it has to maybe go to some specific place or pick up some objects. So you have a argument that correspond to the action and also argument that correspond to the target objects. And in some cases, we also give the agent to pick up 3 objects or 4 objects. And in that case, we also provide the number of target objects to repeatedly execute the command, also as an additional argument. So the goal of subtask controller is to being able to execute this any arbitrary combination of action and target object without seeing all these combinations explicitly in the training time. And second, it has to also somehow internally predict whether it's done with the task or not. So when it's done with the task, then it should give a signal back to the meta controller that it is done with that task. So for this generalization for unseen combination of action and target object, we found that we need some regularizer or some notion of this type of embedding that is able to handle this type of unseen scenarios. The high-level idea is that if you know how to go to some object A or object B, also if it knows how to pick up an object A, then it should somehow know how to pick up object B because of some regularities in these 4 possible combinations. So you can think about some kind of embedding vector. So you can think about embedding for the visit A and embedding for the visit B. So then you can consider a difference between these 2 embedding vector that somehow represents some concept of replacing object A with object B. If you consider this difference between the embedding of visit B and visit A, it should somehow correspond to the embedding vector that is difference between the pickup B and pickup A. So we somehow put some regularities, such as difference between these 2 vectors should be similar to difference between these 2 vectors. And similarly, if you consider task like visit A and pickup A, then the difference between these 2 vectors is basically replacing the action from visit to pickup. And that type of relationship should also hold for this visit B and pickup B pair. So by doing this type of training, we can basically somehow put some constraints that this difference of the vectors should be similar for different pairs. And then the network is able to learn an embedding that can behave well even in the testing time. So if agent hasn't seen this pickup B in the training time, it still be able to somehow have a good embedding for this specific action and target object combination so that it knows how to behave in that scenarios. So there are some details, but high-level idea is that you just want to have some kind of constraint that keeps this difference of the vectors similar between these analogy pairs. And there are some extra constraints so that we want to also push the different embedding or different task embedding to be different enough. So we also push this farther away from 0. If they are similar, then we want to have some kind of constraint that satisfies this parallelogram structure in the embedding space. So with this type of embedding of the subtask, so I just talked about how we can learn a subtask embedding given the subtask argument. And the agent has to take this subtask embedding and take on sequential action to perform, like pick up some object or visit some objects and so on. So it'll just do some sequential decision making by itself, and it has to also decide whether it's done with some specific task. So at the end of its execution, it will say, I'm done with this task. So it will give a termination signal of 1 back to the meta controller. So this is the overall RL objective and analogy making as a regularizer for the embedding space, and also termination prediction as an additional classification problem. So that's how we train this subtask controller. So by doing this, we can generalize to multitasks. So this is able to handle the first generalization problem. So experimental results, these are environment that the agent sees. And the agent can take some actions such as move in different directions or pick up an object facing in different direction and transforming the object, or just taking no actions. And the task is to solve some specific combination of action and target object, such as visiting or picking up the object or transforming the object. We consider also some variations. For example, interact is a kind of a very special type of action. The meaning of interact can vary depending on the type of object. So when you say interact with a sheep, it can be just picking up that sheep, or also for other object, it can be transforming. So basically, this meaning of interact is dependent on different type of objects. And especially in this interaction scenario, the notion of analogy making is even more important because you need to somehow distinguish between these subtleties. And also we consider repeated actions, which means that the agent picks up multiple objects of the same type, and it has to somehow remember number of objects and behave accordingly. And here are some summary results showing that if we compare the analogy making regularizer and with baseline without analogy making, usually agent without analogy making can perform quite well for the training data, but it actually fails really badly for the unseen scenarios. So it doesn't really generalize well to unseen combination of the action and target object. And the object-dependent scenario means that there is a command like interact, which means specific action can be different depending on the type of objects. Again, using analogy making is useful in those scenarios. Another scenario is that when you repeat some actions, we actually provide some subset of these numbers, such as like 1, 3, 5 as a number of repeated actions to take, and then in the extrapolation scenario, we test it on 2, 4, 6, and some other number of repetitions. Again, using this analogy making is useful in that scenario as well. So here are some video. So independent means that you can perform one action to any kinds of objects. It is trying to visit the pig. Pig is around here, so the agent just look at this first-person view environment and goes to the pig. And then at the end of the execution, it says it's terminal. And similarly for different type of objects. And can do this type of generalization. Yeah, so this is more challenging environment than just a grid world style environment because it only sees the partial view. And the high level intuition for this agent is that if it sees some kind of glimpse of the object, probably it will try to go toward the object and take an action. And in this case, we consider the scenario where the agent has to perform different actions depending on different type of object. So when it says interact with X, then depending on the type of the object, the agent has to execute different commands. So pick up like sheep or pig or cat, but for different type of object, it has to transform. So in the training time, it only sees these type of objects, but it has to generalize to unseen object type. And this is actually impossible for the case of just a baseline agent without analogy making. But with the analogy making, you can actually impose some this prior knowledge, such as even though it has not seen the specific combination of the action and unseen object, you can actually put some regularities between these tuples, and that allows the agent to learn this type of embedding that can behave well in the unseen situations. So again, some video demo showing that the agent is able to perform the action, like interact accordingly to different type of objects. And here, yeah, again, the agent has to generalize to executing like repeated action in different number of times. And again, it's able to generalize well if we use this analogy making as a regularizer. So now I'm going to explain about the meta-controller. The high-level idea is that the meta-controller is given a sequence of instructions that it's trying to execute. So in order to do that, it has to take account observations and also the instruction and termination signal coming from the subtask agent. And the job that this meta-controller should do is to update the command to the subtask controller. And also it has to make a decision about whether it should update the command or not. So more specifically, it will take the instruction from this memory, and then it will also choose the subtask argument. And it has a previous context on retrieved instruction and also previous subtask arguments, and basically takes all this information and then make a decision about what new command to issue to the subtask argument. One component here is that since the agent is having this sequence of instruction, it has to somehow decide whether it should move on to the new instruction or just repeat the current instruction and so on. So you can think about this as some kind of a simple convolution operator. So you have a pointer softmax weights that represents the current instruction, and depending on whether it decides to move on to the next command or not, you can think about it as a simple convolution operator applied to this current attention memory. So then it can move the pointer by one, either forward or backwards at each time step. So that's how you can actually update this instruction pointer. And then also the meta-controller has a notion of some kind of a temporal abstraction, which means that it's probably suboptimal if the agent has to decide every time step about this subtask argument. So instead of doing that, it will try to make a decision about whether it should update the subtask arguments, and only update the subtask argument when this decision is yes. If the decision is no, then you can just reuse the previous subtask argument. So this is sort of a binary decision making the meta-controller will make, and then depending on this decision, it will basically reuse or issue a new command to the subtask controller. Okay, so experimental protocol is quite similar, but the agent can now behave a sequence of subtasks. Also, it has to pick up or transform some different numbers of objects when necessary. And again, we only provide some specific pairs of action and object, and also we only provide some subset of this possible sequence in the training time. There is also some additional challenge here because the agent has to deal with some random event. For example, some box that contains some treasure that appears randomly with some small probability. And when that appears, the agent's optimal behavior somehow go to that box and transform it. Then it gives a high reward. So this can be viewed as some kind of interruption that the agent needs to handle. And it has to basically drop what it's doing and then handle this random event. So that also makes this problem more challenging. So as an experimental result, we find that using this type of full architecture that has this temporal abstraction with this hierarchy performs the best. For example, it can do well not only for the training time, but also testing time. So test scene means that the specific combination of action and target object is the same for this scenario, but it is just the arbitrary long sequence of the instructions. But then unseen test environment means that the agent also needs to take actions for the new task combination of action and target object. And compared to some baselines, such as non-hierarchical baseline that have the same architecture as ours, but it just directly makes a low-level decision every time step without learning this type of parameterized version of this subtask controller. That's what we call flat. And also, hierarchical long means that agent is not really handling this interruption. So it just waits until the subtask controller finishes task, and then it will update the task afterwards. So this hierarchical long probably can do poor job when handling the interruption that happens randomly. And another baseline is hierarchical short, which means that it's the same hierarchical architecture as ours, but it doesn't have a temporal abstraction. So it will make a decision about the subtask command every time step. So probably it has a more chance of making mistakes or suboptimal decision because of this lack of temporal abstraction. So at the end, we can see that our full architecture is better than these other baselines. So far, I talked about 3 pieces of work. One on how to make better future prediction and how that can be useful for reinforcement learning, and also how memory can be useful with some very complex environment, especially with first-person view. And third, I talked about some ongoing work on how some temporal abstraction and analogy making can be useful for an agent that is trying to execute the instruction sequence and also trying to solve some multitask generalization problems. So this is the end of the lecture, and thank you so much. And if you have any questions, I'll be happy to answer. Thank you.